Hello everyone, myself Soumya Viji, Assistant Professor, Department of ECE, SJBIT. The subject is Digital Communication and the subject code is 18EC61. The topic of discussion is Digital Modulation Techniques. We discussed about the different types of digital modulation techniques as well their waveforms. Now in this session, I will be discussing about the representation of the signal, particularly for the PSK. In general, when I tell the signal, the representation of the signal in terms of energy, it will be done as S of t is equal to m of t into c of t. Here m of t represents our message signal and c of t represents our carrier signal. In digital modulation, as we know, our message signal will be in the form of ones and zeros, and our carrier signal is a continuous waveform, it is a sinusoidal signal. So, m of t will be either 1 or 0 and c of t can be represented as AC cos of 2 pi fct, a general representation for the sinusoidal signal, AC cos of 2 pi fct. The three parameters of interest are AC, Fc, and if we take the plus pi of t, pi, that is phase value. So, when we substitute the c of t and m of t in this expression, we can take s of t as equivalent to AC cos of 2 pi fct. Accordingly, if I want to find the average power of this s of t, this is equivalent to AC divided by root 2 the whole square. The general equation is amplitude divided by root 2 the whole square. Here the amplitude is AC, so AC divided by root 2 the whole square. Root 2 is nothing but root 2 squared is nothing but 2 AC square. So, AC square by 2 is the final expression that we get for average power of this AC cos of 2 pi fct. This is represented as capital P. But we know that this average power is the ratio of energy and the time, that is E by T. The unit will be joules per seconds. This can be represented in terms of symbol as EB divided by TB for symbol duration t greater than or equal to 0, less than or equal to capital TB. So, P is equal to E by T, that is joules per seconds, equal to EB divided by TB for symbol duration t greater than or equal to 0, less than or equal to capital TB. Now, if I equate the same thing in this expression, this average power AC square is equal to EB by TB, or if I just segregate the terms and take only the AC component, AC is equal to square root of 2 EB by TB. The amplitude AC is equal to square root of 2 EB by TB. We got the expression for the amplitude. Let us substitute this expression in this S of t is equal to AC cos of 2 pi fct. So, the expression of S of t will be equal to square root of 2 EB by TB cos of 2 pi fct. This is the representation of the signal in terms of energy, which we need to consider in all the digital modulation techniques. S of t is equal to square root of 2 EB by TB. Square root of 2 EB by TB represents the amplitude, cos of 2 pi fct. Now, in this expression, the bit duration will be fixed. The bit duration is fixed, that is t value is fixed, hence Fc, that is the carrier frequency, will also be fixed. Since the bit duration is fixed, the carrier frequency Fc is also fixed. Therefore, the S of t can be expressed in terms of basis function as S of t can be expressed in terms of basis function as S of t is equal to square root of EB into square root of 2 by TB into cos of 2 pi fct. Square root of 2 EB by TB is segregated as square root of EB into square root of 2 by TB into cos of 2 pi fct. Here again S of t can be written as S of t is equal to square root of EB into square root of 2 by TB cos of 2 pi fct will be written as pi 1 of t, pi 1 of t. This is the basis function. S of t is expressed in terms of the basis function. The pi of t is equal to what? Square root of 2 by tb cos of 2 pi fct. Here we have written the expression in terms of one basis function. If there are two carrier frequencies, there will be two basis functions, that is pi 1 of t and pi 2 of t. Pi 1 of t is equal to square root of 2 by tb cos of 2 pi fc1t. Pi 2 of t is equal to square root of 2 by tb cos of 2 pi fc2t. Like that, depending on the number of basis functions, number of carrier frequencies, we can write the number of basis functions. Since here only one carrier carrier function is there, we are having only one basis function. This is the representation of the message, of the signal, that we need to consider in all of the digital modulation techniques. It is S of t is equal to square root of ab into pi 1 of t, and pi 1 of t can be written as square root of 2 by tb cos of 2 pi fct. This is the basis function. This is very important that we need to, because this is the expression, these are the expressions that we need to consider again in the mathematical analysis of different types of digital modulation techniques. Now let us discuss about BPSK using coherent detection, binary phase shift keying using coherent detection. First we will discuss about the signal representation of the BPSK. In binary PSK system, there will be pair of signals which are represented as S1 of t and S2 of t. These two signals are used to represent either binary symbol 1 or binary symbol 0. The signal S1 of t is used for representing binary symbol 1. The signal S2 of t is used for representing binary symbol 0. Accordingly, we can write the expression for S1 of t and S2 of t now. For symbol 1, S1 of t can be written as square root of 2 EB by TB, which is the representation for the amplitude in terms of energy, that is multiplied with cos of 2 pi fct. The t value ranges from 0 to capital TB, which is the symbol duration. Similarly, S2 of t will be the signal that is used to represent the binary symbol 0. For binary symbol 0, there is a phase shift of pi radians. So the expression changes to square root of 2 EB by TB cos of 2 pi fct plus pi. Cos of 2 pi fct plus pi. This cos of 2 pi fct plus pi is nothing but minus cos of 2 pi fct. So substituting that, we will get the expression for S2 of t as equal to minus square root of 2 EB by TB cos of 2 pi fct. Again, it is within the symbol duration, that is 0 to TB. This expression is for symbol 0. For symbol 1, we can write that as expression number 1. For symbol 0, we can write that as expression number 2. As I mentioned, TB is the bit duration and EB is the transmitted signal energy per bit. TB is the bit duration or the symbol duration, and EB is the transmitted signal energy per bit. In this expression, the carrier frequency Fc is chosen equal to Nc by TB for some fixed integer Nc. The carrier frequency is always the multiple of this, the fixed integer Nc. The carrier frequency Fc, it is equal to Nc by TB. Nc is some fixed integer Nc. Nc is some fixed integer. Now, a pair of sinusoidal waves that differ only a relative phase shift of 180 degree. We discussed that it is been labeled as equation 1 and equation 2. And these signals, we call it as antipodal signal. The equation 1 and equation 2 are representing the pair of sinusoidal signals which differ in a relative phase shift of 180 degree. They are differing in a relative phase shift of 180 degree. These pair of sinusoidal waves these pair of sinusoidal waves, we call it as antipodal signal. Antipodal signal. Now let us move further and discuss about the next parameter, which is called as signal space diagram. Signal space diagram. From the pair of the equations 1 and 2, we came to the conclusion that in the case of binary PSK, there is only one basis function of unit energy, because there are only two values, either 1 or 0. So only one basis function cos of 2 pi FCT is sufficient. In binary PSK, since we are considering only two values, either 1 or 0, only one basis function of unit energy is sufficient. Only one basis function of unit energy is sufficient, and that basis function is written as pi 1 of t is equal to root of 2 by tb cos of 2 pi FCT, which lies within the symbol duration 0 to tb. This we can take it as equation number 3. This is the equation for the basis function. Basis function pi 1 of t is equal to root of 2 by tb cos of 2 pi FCT. Now the transmitted signals S1 of t and S2 of t, which we have expressed as equation number 1 and 2, can be expressed in terms of pi 1 of t as S1 of t is equal to root of EB pi 1 of t. This is equation 4. S2 of t is equal to minus root of EB pi 1 of t. This is equation number 5. So S1 of t is equal to root of EB pi 1 of t, that is expression number 4. S2 of t is equal to minus root of EB pi 1 of t, this is expression number 5. The signals S1 of t and S2 of t are expressed in terms of the basis functions. Hence, in the signal space diagram, a binary PSK system, it will be characterized by having a signal space which is one dimensional. It means I can take the value of capital N as equal to 1, and it will be having a signal constellation consisting of two message points. Since there are two message points, it is having a signal constellation consisting of these two message points, and I can take that count as m is equal to 2. So it is one dimensional, that is n is equal to 1, and there are two message points in the signal constellation, which is represented as m is equal to 2. Now the respective coordinates of the two message points will be the respective coordinates of the two message points. The coordinate, one of the coordinate is S11, another coordinate is S21. If we write the expression of S11, this will be equivalent to 0 to tb. Integral of 0 to tb S1 of t into pi 1 of t into dt, that is nothing but equivalent to square root of EB. Similarly, S21 is equal to integral of 0 to tb S2 of t into pi 1 of t into dt, that is equivalent to minus root of EB. The respective coordinates of the two message points will be S11 and S21. S11 is integral of S1 of t pi 1 of t into dt, that is equal to square root of EB. S21 is equal to integral of S2 of t into pi 1 of t into dt, that is equal to minus square root of EB. Now as you can see here, this is my decision boundary for the BPSK, decision boundary for the BPSK. There is only one phase, so only one basis function, that is pertaining to pi 1. The decision boundary lies with respect to the zeroth region, greater than 0 message point 1, less than 0 message point 2, and the region of binary symbol 1 is region Z1, and the region of binary symbol 0 is region Z2. So the decision boundary is with respect to the 0 value pertaining to the axis pi 1, that is the basis pi 1. Greater than 0 will be the region Z1 pertaining to the binary value 1, and less than 0 will be the binary value 0, and the region will be Z2. So two regions Z1 and Z2 in the decision boundary. The message point 1 as a value pertaining to square root of EB and message point 2 as a value pertaining to minus square root of EB. It means what is the coordinate value? The coordinate value for the message point 1 is square root of EB and the coordinate value for the second message point will be S21, that is minus square root of EB. Now in this diagram, as you can see, this is the representation of x1 of t, this is the representation of x2 of t. The amplitude is ranging between square root of 2 EB by TB to minus square root of 2 EB by TB. For x1 of t, it is starting at the positive axis, the waveform starting at the positive axis because it is square root of EB, binary value 1, but there is no phase shift. But when I go for the message point 2, that is binary value 0, there is a 180-degree phase shift. It has to start in the negative region. So it is starting from minus square root of 2 EB by TB. This is the waveform that you are visualizing with respect to the bit duration, that is TB, both for message point 1 as well as message point 2. This is about the discussion related to the binary phase shift keying, its mathematical expression, signal representation and the signal space diagram. Thank you.